Now, okay, good to go. Yangge, the stage
Okay,
is yours.
so can you guys see the screen?
Yep.
Okay, so then we'll start. So hello everyone. So I am Yangge Li. I'm a PhD student from the EC department in UIUC, advised by Professor Sayan Mitra, and I'm the main developer of the hybrid system verification tool VERSE that I'm going to talk about today. And today I will do the talk together with Lin Song. So Lin is a PhD candidate in mechanical engineering department, advised by Professor Naira Hovakimyan. So we are going to talk about code level verification for autonomy. So more specifically, we are going to talk about verification tools for performing code level verification for complex scenarios. So this is a joint work with my colleague Haoqing Zhu, Catherine Braut, and Ge Yishen. And this work builds up on prior work by Professor Chu Fan, Professor Sayan Mitra, and Professor Mahesh Vesmanathan. So in this talk, I'm going to first introduce the VERSE verification tool, and the tool is publicly available at this GitHub link. And I will go through a quadrotic example to show how the tool works, and use live demo to show like some capability of the tool. We will briefly talk about background theory behind the tool, like something about data-driven verification. We are going to talk about reachability and sensitivity. And for the last part of the talk, we are going to talk about some applications of the tool. And in that section, and in that part, Lin will specifically talk about an interesting application of using VERSE to verify L1 adaptive controller. So there has been lots of progress in formal verification of hybrid systems with many mathematically interesting ideas, invention of sophisticated data structures and software tools. However, this idea have not made their way outside of the academic labs. Thus, the goal of this work is to make verification techniques more usable. So we are building VERSE to address some of the challenges that arise in verification of complex scenarios with interacting agents. So next, I'm going to briefly introduce VERSE and the verification problem that we are trying to solve. The input to the tool will be the system that we want to verify and some requirements that we are trying to check against. More specifically, we are focusing on multi-agent hybrid scenarios, such as this like two-drone interacting scenario on the right. And the requirements that we are checking against are the safety properties or environment properties, such as like the joins should always separate by some distance. The output of the tool will either be a proof that all behavior of the system meets requirements or provide a counterexample that the system is indeed unsafe. And to solve the verification problem, the basic approach that we are using in VERSE uses like probabilistic sensitivity analysis together with like deterministic reachability analysis. And I will talk about this in more detail in the later part of the presentation. And currently, we are also looking into some like advanced approaches, including like parallelized verification to improve performance, like incremental verification, which saves results from previous verification runs for consecutive verification runs. And we are also looking into like verification with neural network controllers. So now I will briefly talk about how we can create scenarios in VERSE. So consider about this scenario with two joints flying along like three parallel, vertically separated like straight tracks and interacting with each other. An example of the code snippets showing like how this scenario can be specified in VERSE is shown in this top right picture. So a scenario in VERSE is defined by a set of agents, a map, and a sensor and a sensor. So this map defines like a sequences of waypoints or tracks or like some motion primitives. And in this example, the map will define the three tracks that these two drawings are following. The sensor will specify the information available to see one agent about other agents. In this example, the sensor allows each drone to see full states of other drones. And the agent here is a combination of a decision logic and some dynamics. So the decision logic will be written in Python. It's defines some of the high-level decision-making process of the agents, such as under some condition, the drone should avoid up or avoid down. And I will talk more about this in the next slide. And the dynamic contain a low-level controller will specify how the agent can follow the waypoints of the motion, or the tracks of the motion primitives. And in this example, the dynamics is like a 60 quadrotor model controlled by a low-level band controller, like band type controller for following the tracks. And in later part of the presentation, Lin will talk about an example with dynamics consists of like a 18-degree model controlled by L1 adaptive controllers. In this talk, we will use Python simulators as a dynamics. However, Verse also allow black box simulator as a dynamics. Okay, now I'm going to talk about some details about the decision logics. So the example decision logic that we used for this two drawing example is shown in this picture on the right. So the decision, basically what this piece of code says is like each drawing should non-deterministically switch to available tracks above and below if it is too close to other drawing in the same track. So as we can see, this is basically like a piece of Python code. The decision logic is written in Python and can modify agent's mode. And if there exists multiple possible transitions, such as a drawn following the middle track in the previous scenario, can either switch to track above or below. Verse will explore both of these transitions, which we will see later in the result. And Verse also allow user to use Python and any and all functions to quantify over all other agents in the scenario, so that it is able to handle multi-agent scenarios. And the decision logic allow user define functions such as this is close function here, which can help user write more succinct logic to create more complicated logics and scenarios. And the safety specifications for words can be defined using Python assert statements, which means people don't need to learn new logic to do safety specifications. So with this constructed input scenario, words will extract the discrete transition structure from the decision logic for each agent and the map. And this transition structure, together with the dynamics from the agents, can form like a hybrid system. And Verse will verify the hybrid system by building and traversing a reachability tree of the system. The reachability computation can be done using DriveER, which is defined by Chu Fan, or like NewReach, defined by Da Sun. So in addition, Verse internal representation makes it possible to develop new algorithms that exploit such as it can exploit symmetry, similar to the approach in the work by Hossein Sibai and myself, or do incremental verification or parallelization. So in the following slides, I will dive a little bit deeper into how Verse works under the hood. So for the first part, I will talk about how we can convert Verse scenario to a hybrid system. So consider a scenario as C with K agents. So each agent I will have its continuous state space Xi, its mode space Di, a guard function Gi, and a reset function Ri that is extracted from the decision logic. So here for a pair of mode D prime from that's in the mode space Di, we will have the guard function will define the transition condition, and the reset function defines the change of continuous states after the transition. And the agent will also have a flow function, which given an initial state and a mode, and it can return the state of the system at a given time. So the flow function can be obtained from each agent's dynamics. So with the components of the agents defined, we can now obtain the hybrid system HSC equal to X0, D0, GRTL from composition of agents. So the continuous state space X of the scenario is obtained by composing continuous state space of each agent. In addition, we denote an element X in X, a single state, and we say X0 and we define X0 as a set of initial states. Similarly, we can also get the mode space D, like capital D, and a single mode lowercase d, and an initial mode D0. Similarly, for a pair of modes dd prime, we can get the guards like a guard function G and a reset function R for the scenario hybrid system by composing the agent guard and the agent reset. The last part of the hybrid system HSC is TL. So TL is a set of pairs like psi d, where like psi is a trajectory, is a function taking a real value between 0 and t and output a state, which describes the evolution of continuous states in mode D. So given a mode D and an initial state x, like lowercase x in the continuous state space, the trajectory psi should satisfy each agent's flow function for all the time. And here we will also introduce a bit of additional notation. So we will define psi.f state, psi.l state, and psi.l time, the first state of trajectory psi0, the last state of the trajectory psi t, and we define psi.l time equal to t. So with a hybrid system for the scenario constructed, we can now define the execution of the reachable set of the scenario. So we will first define the delta execution of the scenario as a sequence of m labeled trajectory, alpha equal to psi0 d0 to psi m minus 1 d minus 1. So the labeled trajectory should satisfy that the first state of psi0 should in the set of initial states x0 of the hybrid system, and d0 is the initial mode of the hybrid system. And the transition between different trajectories should satisfy the guard and the reset. And the last requirement is the transition between different trajectories should satisfy so the L time for all trajectories except the last one is delta, and L time for the last trajectory will be smaller than or equal to delta, which means the transition can only happen at every delta time. So an example execution of this two joint example is shown in this picture at bottom right. With the execution defined, we can now define the reachable states starting from a single initial state, x0, d0, as reach x0, d0 on Tmax, which is a reachable state, like the reachable states from x0, from the initial states x0, a single initial mode d0 along an execution alpha is defined as all states in this execution until Tmax. With this reach for a single initial state defined, we can now define the reachable states for the hybrid system as the union of all reach x0, d0, Tmax for all x0 in the set of initial states of the hybrid system, capital X0. So now with the set of reachable states defined, we can easily see that to prove safety, we can just check the intersection of the reachable set of the hybrid system and the set of unsafe states is empty. And if this intersection is empty, we can say that the system is safe. And now we will quickly talk about how we compute reachable set in verse. So verse computes a reachable set by constructing a reachability tree using some post operators. So for a pair of modes dd prime, we will now define the continuous and discrete post operators as post count xd equal to x prime, which captures how the continuous states of the hybrid system can evolve starting from a set of states like x in mode d for a delta time to another set of states x prime following the flow function of each agent. And also the post disk operator, which captures how a set of continuous states x can change to x prime while a mode transition happens. With these two post operators defined, verse can construct a reachability tree equal to V, like V, the set of vertices, and E, the set of edges up to a depth M, where each vertex in the set of vertices V is a pair of a set of continuous states and a mode. The root of the tree is a set of initial states x0 and the initial modes d0. And there is an edge from vertex S D to a vertex S prime D prime if and only if the new set of states S prime can be obtained by first applying like post disk on S and then post count. It's currently post count and post disk implemented in verse captures an over approximation of the actual post count and post disk. So in this case, we can show that the reachability tree constructed by verse is an over approximation of the actual reachable sets, which can be used for performing the safety verification. So in the following slides, I'm going to dive even deeper into how verse use discrepancy function to compute post counts. So a discrepancy function beta is defined as a like a uniformly continuous function, such that for any pair of trajectories, psi1 d and psi2 d in the set of TL, and any t in the union of the domain of psi1 and psi2, it will satisfy that the difference between the two trajectories at time t will bounded by the discrepancy function given the first states of the two trajectories as inputs evaluated also at time t. And in addition, we require that the difference between the two trajectories at time t will be So in addition, we require that the discrepancy function that as the initial states of the two trajectories converge to the same points, the value of the discrepancy function will also goes to 0. So this picture on the right shows like how the discrepancy function works. So if we can properly find the discrepancy function and then computing post counts for a set of states x0 defined by like this ball centered at x0 with radius r in mode D can be done easily by first obtain like a trajectory xi0 starting from x0 labeled by mode D. And then we can obtain the discrepancy, like a proper discrepancy function beta. And then an over approximation of post counts can be obtained by adding the discrepancy function value to the center trajectory at each time. So now we want to find a way to compute the discrepancy function with guarantees. And the idea is to learn like a discrepancy function from data. So in a certain mode, let us assume that there is a global discrepancy function, like in this exponential form, like the distance between the two neighboring trajectories are upper bounded by their initial distance multiplied with e to the at plus b. Now, if we can find or learn A and B from the initial simulation data, we will have an exponential discrepancy that at least works for the simulated points. So how we do that? Let us take the logarithm of the inequality. So at any time, the log of the distance between x1t and x2t over the initial distance is less than or equal to at plus b. Remember, we can set those initial state values x10 and x20, and the simulator can return us the value of x1t and x2t at sample time. So we can get these sampled points and find the value of A and B by learning a linear separator. That is, find a line at plus b such that all sampled points lie on one side of the line. And we can prove that using this idea, the tightest discrepancy function can be found through solving a linear programming problem. And this discrepancy function comes with guarantees. So from the original theorem of pack learning, we can get For any epsilon, the measure of the set of simulation points for which AB is not a discrepancy function can be made smaller than epsilon by choosing an appropriately large number of samples. Thus, if the number of samples n is greater than or equal to 1 over epsilon times the natural log of 1 over delta, then with probability 1 minus delta, the algorithm finds a discrepancy function that has an error smaller than epsilon. The sampling number is linear to 1 over epsilon and log to 1 over delta, and in practice, this can be even better. So for example, if we set epsilon equal to 0.1% and delta equal to 1%, and in theory, we require approximately like 4,600 number of samples, but in practice, we showed on many systems that it is enough to use n equal to 20 sample trajectories. The intuition behind is that we are not using these sample trajectories to capture the corner cases. The algorithm is learning the worst case sensitivity of those sample trajectories. So even if none of the trajectories is like a corner case, the resulting overall approximation using the learned discrepancy will bound all corner cases with high probability guarantees. Okay, so that's the end of the theorem part. And for the last part of this talk, I'm going to go back to the examples and talk about some examples and application of words to demonstrate its capabilities. So the first example that we are going to look at is this two-drawing example that we described at the beginning of the presentation. So Words is able to compute an execution of the scenario as shown in this left picture in the middle row. So we randomly sample a point from the set of initial states of the scenario, and we can see in this picture that as the red drone approaching the blue drone, it will non-deterministically choose to switch either to the upper track or the lower track. And the picture on the right in the middle row show the verification results of the same scenario. So we can see that the reachability analysis extensively check all possible execution of the scenario starting from the set of initial states and find potential safety condition violation. So the picture on the bottom left show that we can, like, using the feedback from the verification results, we can now modifying the parameters in the decision logic, and we can improve the behavior of the agents and mitigate the safety violation. And we can see that the red drone will non-deterministically choose to switch upwards or downwards to avoid the blue drone, and the reachability analysis now finds no safety violation. And inverse, the user can easily modify scenario to test more interesting behavior of the agents. For example, as shown in the bottom right picture, we can easily modify the scenario so that the agents are now following this interesting infinity-shaped tracks, and both agents can now have the collision avoidance behavior. And we will further demonstrate this ability through some live demo. So in the following slides, I'm going to run some live demos on some vehicles lane switching scenario to demonstrate capability of words. The examples are similar to the drone example I talked about earlier, but due to simpler dynamics, they can run faster for live demo. The example contains 3 cars with red and blue cars starting at the same lane and green car starting on a different lane. So the red and green car is running at the same speed, and blue car is running at a much slower speed. And the red car can have like a interesting decision logic that it can perform a lane switch when there is another car in front. And all 3 vehicles have some uncertainty in initial condition. And the safety condition is that the red vehicle should be 1 meter away from all other vehicles. So we can easily create these scenarios. So can you guys still see my screen? And is the text big enough?
Yeah, we can see it good.
So we can easily create the scenario, like create this car scenario by setting the agents, setting the map. And now we'll run this scenario and see what the results looks like, and see what the verification results looks like. It should finish shortly. Okay, great. So now we should see the computed reachable set of the scenario is showing in this plot in the browser. And we can see that the red car perform like a non-deterministic like lane switch when it's getting close to the blue car. And the verification result shows that the scenario is safe. And in the second demo, let me really switch back to the slides really quick. And in the second demo, I will show that we can easily change the scenario to see like some interesting behavior of the agents by just changing one line of code in the scenario definition. So basically, we will change the map from this straight line map to like this curved line map. So basically, what I will do is I will just change this to a different map, and let's run the scenario, like verify the scenario again. So this one will take a little bit longer time because of the more complicated map. And let's wait and see what the results looks like. Okay. So now we get the results. So we can see that some interesting behavior happened after we modify the scenario. And we can see that the red car will still try to switch to the other lanes, but the safety violation can happen when the red car is trying to switch to the line, like the track above it. I mean, to the track above it, as the red car can become too close to the green car in the scenario. And another interesting observation we can see is the bottom branch, like the branch where the red car switched to the bottom lane is still safe, and basically we will have the full track. And for the last part of the live demo, I'm going to show that how we can handle some uncertainty in the perception by changing the sensor. So remember that at the beginning of the slides, I talked about that the sensor defines how each agent can see each other. So in this example, we will use a different sensor that adds like a 0.5 meter noise to the percepted position of other vehicles and see how the behavior of agents will change. So let me go back to the editor. Let me first switch back to the initial, like the straight line map, and easily set a different sensor by using like adding this one line of code, 0.5, 0.5. So now I'm adding this, setting this, using this noisy sensor instead of like the ground truth. And let me run the scenario again. And again, we can get the results quickly. It's already, yeah. So here's the results. And if we can easily see from the result plots that with the ends, we can easily see from the plots. And okay, how should I do this? Wait, what happened? And by comparing with the results without the sensor noise, we can easily see that the range of position that the red car will switch lane will be larger due to the sensor noise. But even with the sensor noise, we can see this scenario is still safe. Okay, let me get back to the slides. So in this table, and the plots shows like more scenario that can be verified by words. for example, Words is able to easily create and verify scenario with as much as 7 agents. And we have 7 like interacting agents, and we are able to like verify it in a reasonable amount of time. Like the result is showing this bottom left picture, and it also allows user to employ like to import map from like OpenDrive formats to create complex scenario, like this interesting racetrack scenario. And it also, and as we already see in the previous part, like it creates various different type of agents and different methods for performing like post computations. Like here, we have shown using using DriveER as post computation, and we also can use like NewRich as post computations. And last but not least, Words can still perform well on like classical hybrid system verification benchmark, such as this classical Van der Pol verification benchmark, and also like this spacecraft and gearbox benchmarks. Okay. So in the following slides, Lin is going to talk about an interesting application of Words for verifying L1 adaptive controller. So I will stop sharing and hand it to Lin.
Sure, thanks, Yangge.
Yangge, actually, if I may interrupt, this is Sayan. I don't know if you can hear me.
Yes.
So there is a question about how uncertainty in the initial dynamics is handled. And so you briefly talked about it when you described the post-cont computation and the discrepancy function. So maybe you can just quickly review that. This might be a good time to explain that before going
Maybe I stop sharing.
Okay, so then again, let me share my screen really quick. Okay. Yes. So basically, we will use the discrepancy function to propagate the uncertainty in the initial condition, as shown in this slide. So basically, what this discrepancy function can do is it will be able to give a bound on like 2 trajectories given their initial states. So basically, we will use this discrepancy function to propagate the uncertainty. To propagate like the initial condition, like the initial uncertainty through like the entire time horizon, like through time.
So the question is, hi, Irene Gregory, sorry. It makes perfect sense, right? In terms of your initial conditions being uncertain, parameters, velocity, position. But you also have a couple of other things, right? How well your system follows your trajectory. So it's not just the initial condition uncertainty, it's uncertainty how well you follow a particular trajectory. That's one. The other one is the complexity of your dynamics will impact how, when you're looking at your reachability sets, right? How complex your dynamics potentially change your reachability set.
Yes.
So, I mean, I can make assumptions of how you handled that, but I would love to hear directly from you.
Yes, that's actually a good question. So how we are currently handle it is, so my answer for that is the discrepancy function will capture what's all you just talked about. So if you remember, like we have, like we talked about, there's a dynamics, right? So basically, the discrepancy function will be changed if we change the dynamic, like if we change the dynamics, and if we change the how the dynamics is tracking the reference trajectory. And if that's changed, the discrepancy function will also change, and we will get a different set of reachable sets. So does that answer your question?
Yeah, it does. That's what I kind of assumed you were doing. I just wanted to double check. Thanks.
Okay, sounds good. Yeah, thank you very much. So any other questions? Guess if not, I will hand it over to Lin.
Thank you, Yangge. So Lin, just show the L1 verification results now. Some time.
Sure. You can you see my screen? No. Okay. Hi everyone, I'm Lin Song, working with Professor Naira Hovakimyan, and based on the theory part of the words that depends upon, I'm going to introduce an application that we recently worked on verification of L1 adaptive control. And L1 adaptive control has achieved a lot of remarkable results on experiments, and this is the first time that we do the using existing formal verification tools to verify the features or properties of L1 adaptive control. And I'm going to start with this slide. This is a big picture or architecture of the how we use words library to do the L1 adaptive control verification. And in this pink region, this is a system for the code level verification. This part of the code is work as a simulator, and it is taken as a words library input. And in this specific setting, we consider uncertain system. We consider a joint model and subject to uncertainties. Here, for like implementation inconvenience, we use the parametric uncertainties on the mass parameter, but we can definitely try other type of uncertainties. And L1 adaptive control is capable of handling a broad class of uncertainties and compensated for the uncertainties. And the baseline controller, we use a geometric control, and our control objective is to track a given reference trajectory and see whether the system can handle this case under a large uncertainty. And in this case, we also consider the uncertainty is rapidly changing. And this simulator code is taken as input to the words library. And for the words library, we also provide a verification hyperparameter, such as the time horizon we want to do the verification and step size. And as Yangge discussed about, words library will use a data-driven methods to learn the discrepancy functions based on the simulation trajectories, and use a simulation-based algorithm to compute the approximated reachable states. And this is our approximation. And our recently results has been accepted to the work in progress abstract of ICCPS this year. And I have just uploaded this paper to archive, and it should be available maybe next week. I'm going to introduce the verification objectives we want to achieve using the words library. We want to formally verify the following two important features or properties of L1 adaptive control can achieve. First one is transient performance guarantees. In this case, we consider the uncertainty is rapidly changing, and we can see L1 is capable of doing faster adaptation. And the other property is the delay margin preserved or achieved by L1 adaptive control. For the transient performance guarantee part, we consider a scenario that is an 18-dimensional joint model. And the baseline controller is a geometric control, and we use L1 adaptive control augmentation. And the system is subject to rapidly changing uncertainty. And our expected outcome for the verification is L1 adaptive control's capacity for faster adaptation. It can still track the desired trajectory pretty well, even if the uncertainty is no way to be predictable, and it is rapidly changing. I'm going to introduce this case of the transient performance verification. In this case, we consider Joan is subject to a time-varying mass parameter, and this parameter is specifically unknown to the controller. And we assume the parametric uncertainty or the uncertain parameter has prescribed bounds, and this is so for each time step, the uncertain mass can be arbitrary value within this upper bound and the lower bound. And we also want to mention the uncertain parameter, this mass parameter, this parameter set also evolves with time. And from these two figures, we can see when the L1 is turned off, the system is no way to handle this rapidly changing parametric uncertainties. There's like for example, at 6 seconds, this is a reachable state tube for the Z direction. This tube is very wide and the system becomes unstable. But in this case, L1 can handle very well. And we can see the rich tube is still very narrow, and L1 provides a consistent and satisfying tracking performance, even subject to this rapidly changing mass uncertainty. Do you have any questions so far?
No, Lynn, I think you go ahead and questions
Okay.
in the chat because we have only 15 minutes left. We want to get.
Okay, sure. Thanks. And I'm going to introduce another setting that we want to verify the properties of delay margin preserved by L1 adaptive control. We can guarantee a delay margin in this case. In this case, we also consider the mass is uncertain. That is how we can compute the reachable tube and verify an uncertain scenario. And in this case, we consider the system is subject to a delay in the control channel, and we artificially inject such time delay in the control commands. And our expected outcome from this verification scenario is L1 adaptive control can preserve a delay margin, and it is bounded away from 0. And another thing is the graceful performance degradation provided by L1 adaptive control. That is, say, as injected time delay increases, L1 performance may become worse, and at some point the system might be unstable, but we can guarantee a sufficient margin for that. In this scenario, we consider the joint system is subject to time delay on the control input. And specifically here, we just verify the delay margin for L1 adaptive control instead of the baseline controller. And we implement the verification procedure and a range of time delay amount, and we want to observe the performance. And here is the result for the verification. And this is a different delay amount from 20 milliseconds, 50 milliseconds, 80 milliseconds. It gradually increases up to 150 milliseconds. For this 150 milliseconds, the system can become unstable, but at least for 0.1 seconds or 100 milliseconds, the system can behave quite ideal. It can track the desired trajectory with a consistent performance. And in this case, we verify that the delay margin can be preserved by L1 adaptive control augmentation. And then I'm going to introduce some future directions. We can further deploying features of Words library and collaborating with Professor Mitra Sayan's group. And there are some future directions. One interesting application is verification of L1 adaptive control plus a learning component. One such example we have achieved in our lab is contraction-based L1 adaptive control with Gaussian process regression-based uncertainty. The Gaussian process is used to learn the uncertainties, and the related results has been accepted by Alpha DC 2021. Another line of research, since mode switch is a very important feature of Words, and we can further deploy it or explore this feature for our verification. Currently, we just use a single mode. There's no transition. But we're interested to explore two related problems. One is verify the work on Learn to Fly project. That work is accepted by GGCD 2022. And in this case, we identify the system models based on different conditions, and we switch the reference model. And this is a good testing platform for the verification. And we also consider the vehicle models subject to different road conditions and subject to environment changes. And the related results has been accepted by ACM TCPS of 2023. And we can further verify the robustness provided by our augmentation. And the tool used here is a mode switch feature of the WORS library. And for the last part, we are going to explore the post-disk and post-count, that is a reachable analysis Yangge just talked about, to computer reachable analysis for hybrid systems. And if we use it for one step or short horizon reachability analysis, we can further verify the related work of control parameter tuning process. And this is to make the control parameter procedure, the entire procedure, to be reliable. And we have achieved the control parameter auto-tuning work and published by Alpha DC 2023. And we are interested in further explore this direction. Yeah, I think this is the work I have talked about today. And maybe let's switch to Yangge, and maybe we can keep the questions at the end.
Okay, thanks, Ling. So now I will do a quick wrap up of the talk. Okay. So besides the application that Ling just talked about, there's also some ongoing interesting applications, including like the application of using words to verify like some deep neural network based control by Professor Ornick, and or like using words to verify a reinforcement learning based air traffic management system by like Professor Peng Wei at George Washington University. And there's also a interesting thrust to like parallelize words to improve performance. And during the left demo, I think many of you have already seen like a preliminary version of that. So the summary of the talk. So in this talk we present Verse, and Verse is designed to make like hybrid system verification accessible. It supports using Python decision logic, like non-deterministic agents, like complex scenarios, sensors, like Python asserts as safety specifications, and the ability to import map from OpenDrive formats. And under the hood, Verse uses tree-based reachability, sensitivity analysis for post-counts. It can handle like uncertainty in initial states, transitions, and some parameters. And it also allows user to plug in various post computations, including like drive VR new reach or monotonicity. And in the future, we are currently looking into like incremental verification and parallelization. And also there's some ongoing application of verifying like DRL. And we are also interested in verifying like deep learning, deep neural network controllers using Verse. And we are also interested to hear your feedback about like potential future directions. I think that's the end of my presentation. Thank you very much.
Thank you, Yangge. Let's see if we can entertain a few quick questions here before the end of the hour. We still have 8 minutes. Sayan was responsive on the chat with questions. Thank you, Sayan. I know you are on the airplane. And let's see if we have more questions from the audience.
Hi, Yangge, can you hear me?
Yes, I can hear you.
Oh, well, nice talk, and have a question regarding the last, I guess, future work or ongoing work you're talking about. So there is this, I think you're referring to this DNN verification, and can you elaborate a little bit more on that? So what type of DNN-based control you're trying to verify, and is it going to be something like the reachability analysis that you use for words or something else?
So, okay, so that's a good question. So currently the idea that we have is if we can convert like some deep neural network controller into like some decision tree, and if then we can encode this decision tree as like a decision logic in Verse. And then we will use basically this infrastructure, like the verse infrastructure, to verify this combination of this this controller and the dynamics.
Okay, so when you refer to a decision tree, is it like the different models that you can switch between in the verse library?
Yes, yes. So, so what we are imagining is the decision tree will be like basically the neural network controller will like switch between like different, well, basically determine some different decision logic, like basically will switch between some different actions, right? And if we convert it to a decision tree, it will be some if statements and saying that under some condition, if some if condition, like we will get like a specific action, which we hope it can be fit into like our decision logic.
Okay. Okay. Interesting. I would like to know more because we also have some DNA-enabled control that are being developed in our group. Is there a publication or manuscript that I can read?
No, it's still like pretty preliminary. I don't think we really have anything yet.
Maybe we can take this offline and have a small group meeting between our two groups, Yangge, Linsong, Shang, right? A small, like, maybe Yangge could visit our lab and do the demo in our lab. We'll see the state of art, how far they have come on that. DNN, right?
Sure. Thanks for the suggestion. We'll do that.
Right, please schedule it. More questions? Tim is warning me that we have 5 minutes left in the meeting. I don't know why they put time cap. Irene, are you done with questions?
Yep, I have so far. I need to read a couple of things. I may have some others, but right now, thank you for the presentation. That was very nice.
Right, thank you. Well, I see Kevin has dropped, but let's see if the advisory board, the people. Huafeng, if you have any questions, just let us know. Although I know you work closely with Sayan, maybe it's not that new for you, but.
Yeah, probably just a short question. Can you hear me?
We can't hear you. Your voice comes.
Do you consider some aerospace applications for this verification work? I see the car application and the small drone. I just wonder if you consider some a little larger airplane, autonomous airplanes, networks and reinforcement learning.
I would say that would be, we haven't tried anything yet, but I would say that would be something super, like we are super interested in that, and it would be something that would be nice. Like it would be nice if you can try that. So anything you want to add?
Actually, I can quickly add something to that. Yeah, so basically another part of my research group is using verse to, actually it's a Air Force funded SBIR project in which they're applying the same techniques to fighter class models like F-16 models and multi-aircraft scenarios involving bigger aircraft, as you put it. Right? So yeah, I think, and the transition has been very smooth, right? It took students who have never used this tool before to get up and running with these new models within a week or so. So earlier, every new verification exercise would be like an undergraduate thesis or a master's thesis in some case. But now the usability has improved, at least in our experience.
And once we get Irene's model for this VTOL, I'm sure we'll expand this framework to the VTOL model coming from NASA. We're looking forward to it, Irene.
That'll be terrific, yeah.
If no more questions, we can close the Teams. Just make sure we don't lose the recording so put it on the website because we didn't have many people joining today, including Chris from Lockheed Martin and others. So no more questions, it seems. Huh? Then next time we'll have Petros presenting the developments at UNR with their simulators and flight test scenarios. It should be very exciting. We'll have more live kind of movies and things. That will be April 21 in 4 weeks. It's on your calendars to the best of my knowledge, and we'll use the Teams link again, okay? There is something on the chat. Let me see, what is it? Okay, so just thank you for my reading. Thank you also. See you all on April 21. Okay. In the meantime, questions or anything, let me know. Thank you. Bye.
Thank you.
Yeah, thank you very much.
Hello, Naira.